All right, moving on then. So now we're going to be talking about, I was originally going to talk about nuclear reactor design. We'll come back to nuclear reactor design, but I wanted to talk about nuclear waste because it seemed like a bit more interesting for today's purposes. So in order to talk about nuclear waste, let's go back to what it looks like inside the reactor. Here is your reactor core. Inside the reactor core, you have these fuel rods that are coming down. These fuel rods are going to be filled with your enriched uranium-235. It's mostly uranium-238, and it's got some extra material that's in there to kind of bind everything together. They're Tootsie Roll size, so on my computer screen, it's about this big is a typical fuel pellet, about like that. And then they're piled up in these fuel rods that go into the reactor core. The reactor core is filled with the moderator, so we're going to be talking about light water reactors because that's the most common type of reactor that are out there today. It'll be filled with the moderator, which would typically be water. Well, I did say we were doing a light water reactor, and so that's what it's going to be. The moderator will be this water that slows down the neutrons that come from the fission process. They get slowed down by the water so that they can then be absorbed by the fuel rods, by the uranium-235 in the other fuel rods. Also in here are going to be the safety measures. Some of the safety measures, we'll go into more detail about the safety stuff later on. You'll have the control rods that will absorb the neutrons and therefore shut down the reactor should the case or the need arise. So you just insert these into the container and they absorb all the neutrons. Now fission can't take place. If you want the reactor to run, which is what we want, then we pull these out and the fission of one uranium-235 produces the neutrons that are needed. You slow them down with your moderator, and then the chain reaction is able to continue. All right, that is the basic idea. Over time, what's happening is that the chemical composition of these fuel pellets is changing. So it starts with, we're going to go with 5% uranium-235 and 95% basically of uranium-238. Okay, but over time, we've already seen that when these things break apart, they break apart into daughter particles that are about half the mass. And so the composition, and it's specifically, or it's primarily the uranium-235 that is fissioning. You do get some fission of the uranium-238. It's a non-zero cross-section, but it's tiny compared to uranium-235. So the overwhelming majority, and when I say overwhelming majority, I mean like many, many orders of magnitude more uranium-235 will fission than uranium-238. So over time, this composition of this uranium-235 is going to change. Once you've used up about half the fuel, then it's going to be uranium-235. You'll have uranium-238, which is largely unchanged, but it does change. Then you'll have uranium-235, and you'll have its daughter particles, which is going to be, the cesium and the iodine and the neodymium, or not the neodymium, the molybdenum, and the technetium, and all these things that come out from the fission products. Another thing that's going to happen, you do have these neutrons bouncing around, and even though the uranium-238 cross-section, the fission cross-section might be small, not only does it does have a non-zero fission cross-section, but it also has an absorption cross-section. So there is some probability that uranium-238 will absorb a neutron and become uranium-239. 239. And so you can get uranium-239, you might absorb another neutron and get whatever, is it neptunium 240, you'll get, this will beta decay, then you'll have neptunium-239, then you add another neutron, now you have neptunium-240. So you'll build up one neutron at a time to the heavy stuff and get a bunch of things that are heavier than uranium. And then so these are the actinides, or the transuranics, and then these ones down here, the things that split apart, are the fission products. So let's take a look at a breakdown of how much of each of these substances you get. Hopefully I can find this fairly quickly. It is the nuclear spent fuel composition. There's an image that I can usually find right off, that's the one right there. This is the one I wanted. Okay, so in this case, for this image, they enriched it to 3%. That's still commercial reactor grade enrichment. Recall that it is not bomb, you can't make a weapon out of this, it is not weapons grade plutonium. You could try to make a bomb out of it and it would fail. So you have 3% uranium-235 and 97% uranium-238 over time, and it's over the course of several years. You can see the years on the bottom here. The uranium-235 starts to fission, and you can see that it breaks apart. So it's breaking apart into these daughter particles, or the daughter nuclei, and the composition gets cut down. And it gets cut down exponentially, right? The fission probability is going to be related to the number of particles you have that can fission. And so anytime you have a rate that's proportional to the amount that you have, you're going to get an exponential decline. So this decays away exponentially, and what you get from it is are these daughter particles. So you can see that you have still some uranium-235 left over. Okay, you get some uranium-236, that's uranium-235 that absorbed the neutron and did not fission. Recall that we looked at the difference between the absorption cross-section and the fission cross-section in the first lecture that we talked about. And then you get all these other things. So here's zirconium. You have zirconium in the waste. That's interesting. I did not know that. I guess I know now. Xenon, zirconium, molybdenum, neodymium, cerium, cesium. All of these things come as a byproduct of things breaking apart. Now, there's other products that come out of the nuclear reactor besides these. So there are a number of daughter particles that will come out in addition to the ones that are listed here, but these are the ones that remain because these are the ones that have the longer half-lives. So anytime you have a fission that takes place, all the daughter particles are going to be radioactive to some extent. I mean, everything's going to be radioactive to some extent. Even the neutrons are radioactive, right? Because a neutron will wait for 10 minutes and then it will spontaneously decay. And so everything that comes out of this is going to try to settle down to its ground state, which means it's going to have to go through some kind of decay processes to get down there. Some of the stuff that comes out of that might have a half-life that's just minutes. And so the fission takes place, you have a daughter particle that lives for a couple minutes, and then it's going to decay into something that's no longer radioactive. It's just sitting there. Other things might have a half-life of a year. And so you wait around for 3 years, and well, like after you're done, you wait around for 3 years and all that stuff's gone away. But then still other things are going to have a half-life of 5 years, 10 years, 50 days. So all of these daughter particles in the various isotopes of the daughter particles are going to have different half-lives. So that is something to be, that we'll take a look at, are what is going on with these fission products. Now there's a question that came up here, which one is the most radioactive, and that is going to be the subject of most of what we're talking about, so that will be kind of cool. All right, the other thing that's going to happen, so here's the other fission products down here, and it's a small fraction of a percent. The other fission products, these things here that are in red, so the pastel colors are the fission products, and I misspoke. These are not fission products. The red ones are not fission products. They are the transuranics. So these are the things that happen when you take primarily uranium-238 and you start adding neutrons to it. So you add neutrons to the uranium-238 and it will start to change its composition as well. And notice the stuff that you're getting out of that: plutonium-239, plutonium-240, plutonium-241. You're going to get some, this pink or cyan, whatever that is. Magenta. Might be americium-241. So you're going to get a bunch of transuranic elements, and these are heavier than uranium-238. So these are things that absorb a neutron and then persist. Some of the things that can happen is that, for example, in your reactor, you could take some of the uranium-238, it could absorb a neutron and eventually make its way to plutonium-239, and then that plutonium-239 can actually absorb a neutron and fission. And so some of these, part of the reason that this line doesn't stay horizontal all the way through here, if you start with 3% enrichment and you are fissioning the uranium-235, then one could imagine that this line dividing the uranium-238 and the products of uranium-238 and the products of uranium-235 would run straight across, and that all of these fission products here would actually only creep up this direction into the uranium-235 amount. So like all the molybdenum would come only from uranium-235. But you'll notice that the composition is changing in both directions. Part of the reason for that change is that uranium-238 does have does have a fission cross-section. So some fraction of the time, a neutron will hit the uranium-238 and cause it to fission. It's a small fraction of the time, but it's not zero. Other things that can happen is that in the reactor, you'll generate plutonium-239, and then the plutonium-239 will serve as a nuclear fuel and produce some of these fission products. So there's two things going on at once. Either you directly fission the uranium-235, or you can build up these other things, and some of those can also fission. All right, so these main differences between, well, let's take a look at what's left over in the uranium side. You're always going to have some leftover uranium in your fuel rod. There's going to be some leftover uranium-235, and there's going to be a lot of leftover uranium-238. So the uranium-235 it depletes over time. Eventually, your reactor will shut off because after some number of years, you have half of the fuel in the reactor that you started with. And so you have to take the fuel out and replace it with new fuel that's enriched to the amount to allow the reactor to operate successfully. The uranium-238 is really just along for the ride because it's hard to separate. So you just leave it in there, and some of it gets used and some of it doesn't. And then when you're done, you take the fuel out, and then you have to do something with it. Okay, let me take a look at this question. It appears to suggest that nearly half of the fissions are coming from radium-238 and byproducts. It does look that way. I don't know I don't know the actual ratio. I suspect, I don't have any reason to think that this is wrong, like that these things are the wrong size. They seem to be correlated with the stated abundances that you get. So I think a fairly reasonable statement would be that you get some of that uranium-239 plutonium-239 is made in sufficient quantities that you get basically 50-50 fission products. It's not quite 50-50, but that's what this looks like. I could believe that. I don't know the details, so that would be something to look up in a book. But it seems plausible that would be the case. I suspect then that this plutonium-239 that's left over is stuff that... Oh, that's actually... Okay, so that is kind of interesting. So let's take a look. Maybe we can figure this out. Let's take a look at the absorption cross-section, the fission cross-section of plutonium-239 and uranium-235. So fission cross-section U-235, and let's see if we can get one that also includes plutonium-239. This one does. This one looks like it does. So if I zoom in, they are similar to each other. Plutonium-239 and uranium-235 are similar to each other. That's the red and the magenta. This is actually kind of interesting that there's a peak in plutonium-239 at is this room temperature? This looks like roughly room temperature. That's interesting. So the absorption cross section is almost 10 times better at room temperature for plutonium-239 than it is for uranium-235. That's kind of cool or interesting. One thing I didn't point out, but maybe I should have, all of this big kind of fluffy part here in the middle, that is because of certain resonances. So now you're talking about, like, you have this nucleus that sits there and vibrates and has some probability of absorbing things, based upon the motions of the particles that are in there, the nature of the bonds that are formed and stuff like that. And so there are certain natural frequencies where if a neutron comes in with the energy that corresponds to that natural frequency or that natural energy state in the nucleus, then it's got a higher probability of being absorbed. It would be like saying you have a cloud of gas and you're sending in photons of different colors, so those are the different energies, and there are some photons that are more readily observed than others because there's excited states of the nucleus, for example, that there's excited states of the atom that can absorb that element oh my gosh, come on, Stefan, that can absorb that energy because it corresponds to certain energy levels that are available to the electrons. So if you have a cloud of gas, send in the light, some light will be more readily absorbed than others because of the energy levels that are in that gas. Same thing's going on here. You have a nucleus, which is like a gas of quantum particle, like protons and neutrons that are bouncing around. And so if you send in a neutron of certain energies, then there's going to be some states that are more readily absorbed than others. And so that's what all this fuzziness is. Okay, so if you hit it with the right amount of energy, then it absorbs. If you miss it, then it doesn't absorb. There is going to be some random motion. So you have, especially, I guess this is going to be true even with the solid fuel. So you're going to have random motion of the things. Here's, inside the fuel rod, you're going to have random motions of the uranium atoms and things like that. And that's going to actually spread these resonances apart from each other so that you can actually get pretty good absorption here across a wide range of energies, because it may just so happen that the neutron that's coming in is approaching an atom that is moving towards it, such that it shifts it into that resonance or into that energy level where it can more readily be absorbed. Something to consider with all this. But uranium-239, uranium-235, they both have similar absorption cross-sections for thermal neutrons, and thermal neutrons are the ones that are down here. One thing that I will point out, and this will be important for later, is here's the absorption cross-section for the uranium-238, and notice that when you get to the high energy stuff, that the uranium-238 fission cross-section is similar. It all of a sudden becomes similar when you get to high enough energies. So at low energies, it's got a low fission cross-section, and at high energies, it's got a comparable, not identical, but factor of 2, comparable fission cross-section. And so that can motivate a reactor design specifically around using uranium-238 and the high energy neutrons that come out of this. So we'll come back to that at a later time. All right, that brings us back here. So the statement was that with this spent nuclear fuel, that it appears that there's a lot of nuclear reactions that come from the transuranics, and I think that's reasonable to see here. So you get some absorption, and you make some plutonium-239, and then that plutonium-239 is equally likely to react with the neutrons as the uranium-235 is. And so you get kind of burning of both elements, nuclear fission of both elements. All right, let's see. I say room temperature, but the kinetic energy of the neutrons being emitted don't follow ambient temperature, do they? Linux physics. So that goes back to what I mentioned in the last one, is that I say room temperature. What I mean by room temperature is like thermal temperature, and that's what the moderator does. So here's your reactor core, and you have the moderator in here specifically so that the fast-moving neutrons that come from the fission process are slowed down by multiple bounces with the moderator to where they have energies consistent with the thermal energy of the moderator. So this is going to have an energy of kT. That's Boltzmann's constant times the temperature. And so the neutrons are going to have an energy also of kT after they've had several bounces off of the stuff in the moderator. And in particular, if you're doing a light water reactor, the hydrogen is the best component of the moderator because it's equal in mass roughly to the neutrons. Okay. Let's take a look now at the half-life of these different elements. At what's the difference between the half-life of the fission products and the half-life of the transuranics? So those are two different things. The fission products are when something is broken apart. The transuranics are when something has been absorbed and the nucleus has not broken apart. And those give two different outcomes in terms of what is that nuclear waste? The nuclear waste in general, typically in the United States at least, you take these spent fuel pellets out and then you store them. And that's the high level nuclear waste is the spent fuel rods. And it looks like this. That's the composition. They don't break it apart. They don't reprocess it or chemically change anything. In other countries, France in particular, they do reprocess the nuclear fuel. Because if you reprocess the nuclear fuel, you already have some uranium-235 here. You can just enrich it slightly more. You can remove all this stuff and then basically get more nuclear fuel. There's still nuclear fuel left over in the fuel rod after you've used it, if you can just enrich it slightly more, right? This is already still a factor of, I guess this gets you back down to natural uranium-235, right? In this case, after 3 years. So then you just reprocess it back up to here and run it again. Okay, let's take a look at the the half-life of nuclear waste. And this is not what I was looking for. These will be useful, so I'll pull this one up. All right, let's take a look at this one. And then there's a table that's in some Wikipedia article somewhere that we'll also take a look at. Okay, we've already seen the absorption cross-section, so that's... this is actually an interesting figure. So this figure here shows... Let me open it in a new tab so I can zoom in. Hopefully I can zoom in. This figure here shows where what the neutron energy is coming out of the reactor. So I mentioned that it's, the end of those previous plots is up here. So that's the energy that comes that the neutrons have when they come out of the reactor, and then you slow them down so that it interacts down here. All right, back to this other picture. This we've already seen. So this is the distribution of the daughter particles that come out from a fission. And here, this is the one we're looking for. Okay, this is showing the radioactive, like how radioactive the fuel is or the byproducts are. The sum of all of the radioactive compounds in the spent nuclear fuel. So you have the spent nuclear fuel, that's your nuclear waste, and it's radioactive. And it's radioactive for a variety of reasons, namely the radioactivity of all the elements that compose that spent fuel. And so everything that comes out is radioactive to some extent, at least at the beginning, and then it's going to decay over time, but each element or each isotope has its own half-life that it decays on that time scale. And so the things that contribute to the overall radioactivity of the fuel over a long time period, and so this is measured in years, the things that contribute initially are everything, and then as the most radioactive material decays away, then they're no longer a factor. So for example, let me show you what I mean by that. Suppose you have two elements that come out of your fuel. Let's suppose that you have three. So this is the total radioactivity, total. And let's say we have three elements that come out that are radioactive. You have like super high radioactive, we have regular radioactive, and we have slow radioactive. Okay, so the super high radioactivity will have a half-life of like 1 year. The regular radioactivity will have a half-life of like, well, let's go with, instead of a year, do I want to do a year? Yeah, we'll go with a year. The regular one will have a half-life of like 10 years. And the slow one will have a half-life of like 1 billion years. Okay? Let's say instead of 10 years, let's go with 100 years. So now we're going to plot this at 1 year, 10 years, 100 years, and 1 billion years. We don't have to go to 100 billion years. Let's go up to like 1,000 years. So ignore this hatching there. All right, what's going to happen? Well, the sum is going to be well, we'll find out what the sum is in a moment. The super radioactive stuff is going to start up here, and it's going to decay away fairly quickly so that half of it is still there. Half of it is there after 1 year. And it's going to decay exponentially, but that's too careful of a line for me to draw. If I plot this, I guess, on a log, this is a log-log scale. Anyways, it's going to decay, on a log-log scale, it's going to decay like this. So if this is the log on this axis and that's the log, it will decay away like that. The regular stuff has got a half-life of 100 years, so it's going to decay away if it starts with the same amount on some time scale that looks like this. And the slow stuff that decays over a billion-year lifetime, it will decay away like this. Okay, so the total is the sum of all three of these parts. So it'll be 3 times as high. 3 times as high on a log scale is going to be like up here. It's going to be 3 times as high. This stuff's going to decay away first, and then this, and then this. Okay, the issue is that you don't always have this, the amount of decays that you get, the more radioactive something is, the faster it decays away. So if you start with equal, this is equal radiation coming from a given substance. It's not equal mass. If you divide this up by the amount that you have in each thing, you're going to end up with a graph that looks slightly different. You're going to end up with like the total number of decays. So if you have something that's the equal amounts of something, and one of them decays over the course of 10 years, and the other one decays over the course of 1 year, then the one that decays over the course of 1 year will be 10 times as radioactive as the one that decays over 10 years. So it's going to dominate the number of decays. So in that case, you're going to get, the actual curve is going to look something like this. You've got one like this, you got one that's down here, this is with equal amounts, and then you've got the one that decays over a billion-year time scale that's going to look like this. So when you add these things together, you're going to have some curve that goes like this, like that. And you're going to have these bends in the sum of the radioactivity is going to bend as this substance, the most radioactive substance with the shortest half-life, decays away, and then the stuff with the next shortest half-life dominates the radioactivity signal, and then the stuff with the next shortest half-life dominates the radioactive signal. So that's what we're going to be looking at in this figure. The short half-life stuff that's most radioactive is going to decay away fairly quickly. I mean, some of the stuff is going to come out that's going to decay away in minutes. Other stuff is going to decay away in days. The only things that really matter for long-term storage, or for the typical person, is what are the things that decay away on the lifetime, on the scale of like a human lifetime, 100 years or longer. So that's what's going to show up in this figure, is the stuff that is 100 years or longer. So anything that decays away on a month-long time scale or a year-long time scale is already gone by the time you get to 10. So here's the total radioactivity, the total number of decays that you get. And the first things that you have here are the cesium-137 and strontium-90. And notice that they decay away on similar time scales. And they dominate for the first few hundred years. Those are the things that dominate the radioactivity, is the fission products, specifically these two fission products. The rest of them are gone already. Then, okay, there's a couple exceptions. Technetium-99 apparently is an exception to that, and cesium-135 is another exception. Okay, but these two have shorter half-lives and therefore dominate the radioactivity early on. Then you have another, the transuranics, and those have different properties. They tend to live longer. And so americium-241 is here. You got americium-243, plutonium, neptunium, and they all have much shorter half-lives, or I'm sorry, much longer half-lives. They're lower radioactivity, longer half-lives. And so at later times, those are the things that dominate the radioactivity of the system. Terabecquerel, let's see, our terabecquerels decays per second. So that's what this is given, terabecquerels. The becquerel is some unit that is important for nuclear engineers that I don't really, but it is, you're right, it is related to decays per second. All right, so I can't explain why this thing turns over like this. That's a little weird that it does that. Maybe it could be that it just, I have no idea. I have no idea why this curve makes that shape. These should all be, it may be that you have, when you're in that fuel rod, that you can excite certain decays from something like, otherwise I can't figure out why this would increase here and then decrease. Anyways, they have reasons for these curves. Hopefully they weren't drawn by hand. Some of them do look like they were kind of drawn by hand, but don't know. All right. Nevertheless, that's the point here, is that there's always going to be some different element that is dominating the signal at a given point in time. Now, if you look at this uranium ore equivalent up here, this line, that's kind of the line where you don't really have to worry about it anymore, because now if you just take uranium ore, it can be sitting out on the ground, and it's not going to be a real health issue to have it there. And so once the spent nuclear fuel drops below the uranium ore equivalent, then it's essentially safe. Another and probably better way to measure the safety, or at least conceptualize the safety, because I mean, no one likes to hear, oh, uranium, this is as radioactive as uranium. Instead, a better thing to think of is, when is your nuclear waste as radioactive as living in Denver? So Denver being relatively high in elevation, also being surrounded by, I don't know what, mountains or whatever. The elevation, I think, is the thing that dominates it. But when you live in Denver, you're actually exposed to radioactivity more than the typical American. And that comes from all sorts of things, like cosmic rays coming in. I suspect that there's stuff in the minerals. There might be high amounts of radon trapped there or something like that. But Denverites are, in general, also more healthy than other people in the country. So it's clear that once you get down to a dose, like exposure to radioactivity that is on the level of Denver, that you are no worse off than anyone else in society. And so when you are thinking about spent nuclear fuel, what do you do with it, and how do you treat it? The thing to keep in mind is, at what point is the spent fuel similar, if you were to swallow it, is it similar to living in Denver? Or if you were to paint the walls of your house with it, at what point is it similar to living in Denver? Because at that point, then it's clear that there's no detrimental effect to your health. It's going to depend upon how long it's been available to decay. And in particular, the most important thing is to get rid of this cesium-137 and the strontium-90, because that dominates the signal by, look, this is a 1 here, and if you come up to this 10 to the 4, that's 10,000 times more energetic, or like more radioactive than this 1 terabecquerel. So as far as uranium ore equivalent, it's going to be what, almost 500, it looks like. There's 10, 100, yeah, it's about like 500 times. So 500, the uranium ore is going to have some level of radioactivity. The radioactivity from the cesium and strontium is 500 times more, there's more decays than what you get from just uranium ore that's there. And that's going to persist for, it looks like, about 100 years. Once you reach 100 years, then things are all kind of comparable to each other. So you need to be able to store something for 100, maybe 200 years. So let's take, and that's something that we can do. We know how to store things for 200 years, right? We have documents in the archives that are 200 years old. Some families have books in their house that are 200 years old, right? The family Bible from a long time ago. There are some homes in the United States that are 200 years old. There's lots of buildings in the United States that are 200 years old. There are buildings in France that are, churches that were built in the 900s. And so we can store things. We know how to deal with things on the order of a few hundred years. The Magna Carta, we have copies of the Magna Carta, and the Magna Carta is from 1200 something. So that's almost 1,000 years. Okay, things that are longer than 1,000 years, we've kind of lost touch with those civilizations. There aren't many things that have been kept, well contained for 2,000 years or 3,000 years, right? We're finding archaeological sites where they were stored, but we're coming back and rediscovering those things. They haven't been consistently kept and under surveillance, appropriate surveillance over that time. So 1,000 years, that's probably the most that we can do, or at least most that we can claim to do given our history. But a few hundred years is something that we can do relatively easily. There are companies that are older than 200 years old. So if we can store something for a few hundred years until these things have died away, then we've already gotten rid of 99% of the radioactivity of the nuclear waste. The real issue is these long-lived ones here that still put you above the threshold. So let's take a look at the details of these things and see what it is that's contributing. What I'm looking for is a table in Wikipedia that shows, so not an image, we'll go with all, and see what it looks like. Hopefully this has the table in it. This is the table I was looking for. Yes, it does. Okay, so here is the table of fission products and actinides. So these are the two different things that come out of the spent nuclear fuel. It is not that. It is not that either. It is this one. So we want to look at these transuranic elements, the ones that are in red, and compare that to the fission products that are up here. And let's see, where did it go? Here we go. So these are the fission products. The fission products either have half-lives that are decades. So strontium has a half-life of like 30 years, and cesium has a half-life of like 100 years. So these ones that are decades, those are the things that are going to dominate the radioactivity of the nuclear waste for the first few decades, and maybe 100 years, maybe 200 years. It's going to be dominated by this. There's no fission products that are between 100 years half-life and like 100,000 years half-life. Okay, so there's nothing here that has these intermediate length half-lives. There are some things that have half-lives on the order of like 1,000,000 years, but if you have something that's radioactive on the timescale of 1,000,000 years, it's decaying so slowly that it doesn't really add anything to the ambient environment, right? You can just eat bananas, and you'll get more radioactive exposure than you'll get from having these things sitting around because their half-life is so long. So the really long half-life stuff isn't stuff that we have to worry about because their radioactivity is really low. A long half-life implies low radioactivity. Short half-life, high radioactivity, long half-life, low radioactivity. So if we have things that are stable for 1 billion years, then you don't have to really worry about it at all. Okay, so these things, these fission products, these have long half-lives. We don't have to worry about those. They don't contribute to the radioactivity in sufficient amount. These short ones we do have to worry about, and they will live for, we're talking a couple of centuries at most, before they've decayed away to the point where we don't have to worry about them anymore. Okay, for the actinides, so these are the transuranics that come from the absorption of the neutrons without a subsequent fission. These are the things that are most concerning, because these have half-lives of like 1,000 years or 2,000 years. And so in order to wait around for them to decay away, you're talking 10,000 years. And humans we have no evidence that we can do things for 10,000 years consistently from one thing to another. So these are the things that need to be dealt with. One of the things to consider is if you look at, if we take again a look at this figure, if we were to take the fuel, somehow take the fuel and separate out, because these have different chemistry, right? You can do chemistry on this to separate out the different products. Now, it takes energy to do this chemistry. You have to separate it with some, pulverize it or do whatever you got to do. And then you have to titrate, and you have to hire a chemist, and the chemists are expensive, despite the fact that nobody really likes them. You have to extract all this stuff through a chemical process, but it could be done because the chemistry of cesium is different than the chemistry of plutonium. So you could separate these chemically from each other, and then you have a separate, relatively small abundance of, say, cesium that you have to worry about. So it's only 0.28%. So if you immediately reduce the nuclear waste from being 100%, which is everything that's in the fuel rod is currently high-level nuclear waste, you extract the part that's dominating the signal, which would be the cesium and the whatever the other one was, strontium. So you extract those two things, and now you've got 1% of the waste. You've automatically reduced the waste from 100% to 1%, or even less than 1%. Okay, and then you can store them separately. Like you can say, these are the hot radioactive stuff that we need to worry about. We'll separate it completely, but it's only 1% of the mass of what you started with. At the same time, you could also separate out the plutonium from the rest of this. You can use the same chemical processes that you would use to separate plutonium from uranium in general, and now you've got the actinides, or the transuranic elements, also separated out. And so I was even wrong. If you separate the cesium, you're reducing it not by a factor of 100, you're reducing it by a factor of 400. So you have 0.25% of the nuclear waste if you separate it out this way. All things pulled together, if you separate everything that's going to contribute meaningfully to the radioactivity of your waste, you're probably looking at 1%. So if you immediately reduce by a factor of 100 the volume or the mass of the nuclear waste. And you can even separate those further, because the way that you would store something that decays over the course of 100 years is different than the way that you would treat something that decays over 10,000 years. And so you would come up with different storage techniques and further kind of divide the nuclear waste. So that would be a way to do this more efficiently. Now let me go back to, was it this one? Yes. So these are the things that have the troublesome half-lives, because they have half-lives that are longer than the typical human civilization, and they can stay radioactive for a long time. And here the americium-243 and americium-241 are the ones that are probably most important in that mix, because those are produced in the most, those are the most abundant things. Americium-241, I should point out, it's also not like all these things are completely worthless. There are good uses for some of this radioactive waste. So, for example, technetium-99 is useful for medical purposes, right? You do medical imaging using radioactive material, so radiochemistry, radionuclear medicine. So you need to image something in your chest, and you can breathe in. I think with the technetium, it's usually a pill, and so you're looking for things in your lymph nodes. So you swallow this pill, and then you digest it, and it tends to coagulate in different parts of your body, and now you have a radioactive source from that part of your body, and you can use that radioactive source to image what's going on there. So there are lots of uses for all sorts of things that come out of nuclear reactors, including, all sorts of things that come out of nuclear reactors. Not only the fission products, but also the actinides. So americium-241, if we look at the cost per gram of americium-241, I think it's $1,500 per gram. $1,500 per gram for americium-241. Okay, it's not easy to get because you have to get it from, well, in this case, you have to get it from fuel reprocessing, but it's not like a worthless stuff. It's worthless when it's embedded in this Tootsie Roll sized fuel pellet and unavailable to use for other purposes. But if you were to separate it out, it does have some value. So this is used in smoke detectors. You have a smoke detector will have an americium source, and then when the smoke particles get in there, it shuts off the ability to detect things. It's probably it's an alpha emitter, because all things at this level are alpha emitters while there's an airplane flying right overhead, just for everybody's listening enjoyment. It'll be an alpha emitter, and so you have smoke particles go in there that can disrupt the emission of these alphas and set off the smoke alarm, for example. So this is has more than cocaine. Yeah. So if you were to all of a sudden dump, a ton, 1,000 kilograms of americium on the market, yeah, it would change the market price for some of these things. But it doesn't mean, all that would do is make them, there may be other things where you could use americium-241 besides building smoke detectors that currently aren't commercially viable because americium's too expensive. But you could imagine if the price of americium were to drop down by a factor of 10, so that's only $150 per gram, then there might be other products that you could use them in that would be useful to make life, liberty, and the pursuit of happiness more available and accessible to a wider variety of people. Okay, so how would you buy or sell americium-241? Probably with very special connections. All right, so that is, even though we have these things in the decay products, in the nuclear waste, they're only useless as long as they're mixed in with other things that aren't useful. That as long as you can't get to it, then you can't use it for anything. But it is conceivable that there could be a market for this stuff. Right now, it's just that it's probably too expensive to pull it out. It's not worth it to pull it out because you wouldn't be able to sell it for as much as it costs to remove it. This is a place where the next generation of nuclear reactors, which we haven't talked about, but we will get to, the next generation of nuclear reactors can process the fuel in real time and extract these things from them so that it's not embedded in these fuel pellets that we have to store for 10,000 years. Okay. All right, so that is the things to look at. With the nuclear waste, the fission products either have short half-lives and therefore is a more practical problem for how to store them, or they have long half-lives, in which case we don't have to really worry about them. We can just kind of spread them around. All you have to do is diffuse them. In this case, if you diffuse them, then the radioactivity drops down as well because the density of material isn't that high. Or you can store it in some container. It's the actinides that are the real troublesome problem. And so if we go back to this plot, it's these things up here, this americium in particular, some plutonium, that are making it so that the stuff is dangerous for a longer period of time. But if you eliminate the cesium and the strontium, then you've already changed the nature of the nuclear waste, at least for the next 100 years. Okay, so that is the types of nuclear waste that are produced from the fuel itself. There are other forms of nuclear waste that are generated from a nuclear power plant. For example, the equipment that you wear while you're working in the plant, if you have to go in and remove the fuel rods and lick them or whatever, the stuff that you're wearing while you're doing that is also considered contaminated, even though it's probably in general very, very low level contamination, but it's considered contaminated, and so that gets stored as well, generally along with the other things. It's stored differently, but it's something that is stored and buried in containers and stuff like that, so that it's doesn't leak out into the water. None of this stuff is glow in the dark ooze that you see in the Teenage Mutant Ninja Turtles videos. All of this stuff is generally in solid form. Well, it's all in solid form. Okay, there was something I was going to mention about the nuclear waste that had to do with something, and it was really interesting, and I don't really remember what it was. If I can remember what it was while I'm answering questions, I'll bring it back up. All right, let's see. Is sending the waste into the sun possible? So that's a question that gets asked a lot. Can we just send the nuclear waste into the sun? The answer is yes, we could. However, in order to send the nuclear waste into the sun, you have to build a rocket that can deliver it to the sun. And it becomes really expensive. It's less expensive to do something else with it than to put it, to send it to the sun. If you're wanting to use nuclear energy as a means to combat climate change, then the amount of carbon dioxide it would take to launch the nuclear fuel into the sun is probably more than what you save by having the nuclear fuel there. And you can tell that by the cost, right? As soon as it becomes more expensive, it implies that the carbon footprint is larger. So, all right, let's see. And there are many tons of this. Now, I will point out that the amount of nuclear waste is relatively small. So if you look at like the nuclear waste repositories, and we'll do another one about like nuclear waste storage later, another stream about that. Nuclear waste repository France, for example. It looks like this. Oh, that's what I was going to talk about. I'm glad that this reminded me of it. Okay, so these are the kind of waste facilities that you would expect to see in France. No, I don't want the cookies. I refuse cookies. Where's the image? It looks like this. A lot of times they're kind of embedded in a glass and then stuck underground. So this is going to be, what, like almost a half a century of nuclear waste in a building. Compare that with any other type of electricity generation, and nuclear waste is way, way smaller, like way, not even comparably smaller. It's an order of magnitude or more smaller. This is dry cask storage, so this is the kind of storage we currently use in the United States of America. Oh, this actually looks like it shows what it looks like on the inside. So let's take a look at that. So dry cask storage, let me get rid of this one. On the inside of the cask, it's surrounded by some kind of cement. These containers are incredibly strong. They'll put them on they'll like have them set across a train track, and they'll drive a train into it and smash into it, and I'll try to look up these videos and share them at some point. They'll smash a train car into it, and it'll just kind of tumble around. It doesn't break. They'll drop it from airplanes or whatever, and nothing happens to them. These are incredibly strong. You have your fuel core in here. You can see all the fuel rods in there. They'll embed it in something that makes it difficult to extract, to pull back out and repartition or whatever. They basically make it almost impenetrable. And this is going to be for 50 years of nuclear waste is right here. Okay, compare that to 50 years of waste from a coal plant, or 50 years of waste from a natural gas well, or a natural gas well, or a set of natural gas wells that provides an equivalent amount of energy. That's the thing to compare it to. Compare that to the amount of waste from just solar panels. If you did the solar panel waste for a square kilometer of solar paneling over the course of a century is going to be probably bigger than this by a fair amount. This is like one wind turbine blade in the amount of waste that you have here. It might be more massive than a wind turbine blade, but in terms of size, this is smaller than a single wind turbine blade by a long shot. So what I was going to say is that when you have, do I have time to get into this? Yeah, I guess I do have time. So this will be the last thing that I cover today, is what happens when you first pull the nuclear waste or the nuclear fuel rods out of the reactor. So let me get rid of some of this stuff. Except that, I'll keep that one up because that's going to be useful. So when you first pull the nuclear fuel rods out of the reactor, they're hot. Okay, you have lots of decays of a lot of the fission products. This one just shows cesium-137 and strontium-90, but you have all these other products that are in there that are decaying more rapidly. So it's really hot. It's really radioactive when you first pull it out. And you have to cool them down. So you pull the fuel rod out, and it's just, here it is hanging from your crane. Here's your crane that's holding it up in the air. And you're like, okay, what do I do with this? Well, you can't just set it out there in the middle of whatever. You can't just lay it on the floor, because it's radioactive. So there's going to be all sorts of energy that are coming out of here. Now, the core itself a single core might produce a gigawatt. Okay, so one core with all of its fuel rods is going to produce a gigawatt of power. And that's a lot, right? That's a typical home is around a kilowatt. A rough estimate is about a kilowatt for a home. And so a gigawatt is what? 1 million homes. So this power plant can power 1 million homes. You pull it out, it's no longer producing the fission, and so it's no longer able to generate a gigawatt. However, the radioactivity that comes out of it still might be something like 10 megawatts, especially when it first comes out. This will decay over time. It will get colder and colder and colder over time as the nuclei exhaust themselves, breaking apart or like decaying. But it might come out at 10 megawatts. 10 megawatts is still a lot of power, right? If you look at a 100-watt light bulb, how many 100-watt light bulbs is 10 megawatts? That's what, 100,000? 100,000 to go from, does that give me, yeah. So it's 100,000 100-watt light bulbs. Okay, that's a lot of power that's still coming off of this thing. Imagine how hot it would be to have 100,000 100-watt light bulbs right next to you. You get a tan fairly quickly. So you can't just set it on the ground and say, okay, we're done. You have to do something with it while the fast decay, like the most radioactive stuff, decays away. Because that's the thing that's dominating the amount of energy coming off of this thing. So what you do is you stick it into a swimming pool. You put it in a swimming pool. You're like, hey, you cool off in this pool. We'll circulate water around. If you just put it in the pool, 10 megawatts is enough to evaporate water fairly quickly. So you put it in this pool and all the water evaporates, and then you have to come up with, you have to keep refilling the pool. So you'll circulate water around in this thing over the course of several years as the most radioactive material decays away. At that point, you're only left with the longest half-life things, which are no longer on here. The longest half-life things, which is going to be these ones. Okay, everything else is decayed away by this point. So you might have to store it for 10 years. Okay, that's fine, right? Houses are 20 years old. There are lots of warehouses that are older than that. So here it is. So you're going to circulate water around in here to keep the fuel rods cold so that it doesn't melt through the cladding and stuff like that, and it doesn't become a bother. So this is a short-term storage, and that's just to bring the fuel down to to a level where you can put it into some other kind of storage facility. So it doesn't contaminate the water. As long as the fuel is contained in the rod, then there's no contamination of the water. Okay, you may, because most of the stuff that's going to come out of here are beta particles. So most of the emission that's coming out of the fuel is going to be beta. So there's going to be electrons from the fission products, and you'll get alpha emission from so I guess that means you're going to get all three. You're going to get alpha emission from the transuranics. You're going to get beta emission from the fission products. Okay, but those the alpha particles are just going to bump into stuff, and then you're going to have a supply of helium, not a very big supply, but a small supply of helium that's going to be bubbling out of this pool as the alpha particles escape. If they can even escape the fuel rods, because the fuel rods themselves, alpha particles are fairly easy to stop. You can stop alpha particles with a piece of paper. So I suspect that the majority of the alpha particles are going to be still stuck inside the control rods or the fuel rods themselves. The beta particles will make it out of the fuel rods. But they'll be captured, they get absorbed fairly readily in water as well. So it's conceivable that you could go through inverse beta decay and produce a radioactive oxygen atom or something like that, but it would be pretty rare. So you don't have to worry about that too much. So that's what you do. When you look at for example, let's look at Fukushima. Reactor design. Spelled that wrong. Design. Let's see if this has the images that we're looking for. And I'll show you, well, we'll see where they store the fuel rods as they're cooling down. Okay, here's the one that I want to look at in a new tab right there. Okay, I guess we'll zoom in. Okay, this is the Fukushima design. And up here, so here's the reactor core. This is the building around it, and this is the containment building, which I haven't really gone into detail about yet. That when we do reactor design, we'll talk about the containment building. But there's the reactor, there's the containment building, and then it has these pools of water. Service floor. So this is the floor that you walk around on when you need to get into the core, when you have to do things to service the containment building or whatever. This thing up here at the top, spent fuel pool. This pool of water, and presumably that looks like a pool of water as well. This is where they would take the they would put the spent fuel. So here's a crane system. They bring the crane over, they open up the top of this, they pull the fuel rods out, and then they move them over here and they drop them down into this pool. And that pool has water circulating in it. And then they, bring a new fuel rod in, drop it into the system, seal the top back up, and these are the fuel rods that need to stay in here for like 5 to 10 years, something like that, until they're cold enough that you can put them in a different kind of storage. So as you're confronting elements with different half-lives, you put it in a different kind of storage container. So that's where you put it for the moment. And this was actually the issue that caused the explosions at Fukushima. It wasn't the containment buildings. It was this right here. It was the spent fuel that is decaying over time. And the reason was that this requires pumps to circulate the water, and then the pumps to circulate the water turned off, and so all the water evaporated and produced steam. And that steam, it was hot enough to dissociate the oxygen from the hydrogen, and the oxygen would bind to the zirconium that's in there. Also, one of the byproducts of the spent nuclear fuel is also some zirconium. There's also zirconium cladding in there that would absorb to make zirconium oxide, leaving the hydrogen there to do whatever it wants to do, which is to collect in this upper floor. And then when you have a spark with this hydrogen around and the oxygen available to you, then you get an explosion. But it's a steam explosion. It's an explosion from hydrogen combining with oxygen to make the explosion. It's not a nuclear explosion because it's not a nuclear bomb, because you can't make a nuclear bomb out of something that's only been enriched to 3%. So that's what was going on in Fukushima. That was the thing that they were most worried about putting water on it, was putting water on this stuff, which is the spent nuclear fuel rods. So you'll find these kinds of pools. So if we look at a spent nuclear fuel pool, all reactors are going to have these kinds of pools in them. So there you go. So there's some right there. Here's another one. It looks like you can fall into it and you're probably still going to be just fine, because there's a lot of water between you and the core. The alpha particles are going to be stopped almost immediately, and the beta particles are going to penetrate a meter into the water, something like that. So it might be warm, but you're not going to die. Okay, so this is what the pools look like in these different containers. And that's just until it cools off. All right. Any questions on that? Let's go through the questions, and then what are we going to talk about in the future? So, in the future, next time I'll probably go into, I guess, reactor design next time, and then we can start talking about. Well, that's what we'll do next time. Okay. Is the containment still intact? So for Fukushima, the containment building for Fukushima is still intact. The containment buildings are like almost indestructible. They're probably the most strongly built things, especially for commercial purposes, that we have in the world, are nuclear plant containment buildings. Would jumping into the cooling pool be terminable? You probably would. If you jumped in without permission, you probably would get fired. Could a Denverite drink the water? Yeah, probably. Let's take a look real quick and see what is the nuclear exposure. Nuclear exposure in Denver. American city more radioactive than Chernobyl? Question mark. Denver. Let's see what kind of images we have. There might be something useful here. Not seeing something that is promising. Radiation exposure examples. Let's try this one. Open image in new tab. What do we got here? Annual dose in millirem. Maximum permissible occupational exposure 5,000 millirem. Natural exposure in mountain regions of Brazil. Average occupational dose for hospital radiologists. So that's 1/10 of the maximum thing. U.S. average total exposure, natural and medical, is 200. And this is annual dose. Proposed limit on population average non-occupational. What? Proposed limit on population average non-occupational radiation. I don't know how you can enforce that. U.S. natural radiation exposure is 20, And it doesn't show here what you get in Denver. So let's see radiation dosage in Denver. It's like picocuries. It's a number that some people use and others don't. Let's see if it says what it is. Millisievert. There's some conversion between sieverts and something else, and I don't remember what it is. Okay, let me go back and do it in rem, or in millirem. In millirem. Average annual radiation dosage, radiation fact sheet. Will this do it? Where do you live? Let's see if where we live. Cosmic radiation from space, elevation. So we're looking at this one. Denver, Colorado Plateau. There we go. That's what we're looking at. Do I live in a stone, brick, or concrete building? We'll say yes. We'll say that I live in a stone or brick house. Other sources. Miles traveled by jet plane annually. Let's say that you take one trip a year. Do I have porcelain crowns or false teeth? Do I have gas lanterns mantle when I camp? Am I camping? The gas lantern mantles, I think they have thorium in them. Do I wear a luminous wristwatch? Yeah, we'll say I wear a luminous wristwatch. Do I watch TV? No, I don't watch TV. Do I use a video display terminal? Yes, I do that. I watch Twitch, not TV. I have a smoke detector. I have probably several smoke detectors in my house. Okay. And do I live within 50 miles of a coal-fired electricity utility plant? That will be yes. Go. Let's see what happens. What do I get? I'm at 400 millirem. Okay, in Denver, Colorado, I'm at 400 millirem. Now let's go back to what they're saying here. The proposed limit on population is half of what you already get in Denver. Okay, so a person in Denver is getting 400 millirem. That should be like, once your spent nuclear fuel gets below 40 millirem or 400 millirem, then you're in Denver. All right, let's see. Let us go now to the questions, and then we'll wrap it up for the day. The spent fuels have such distinct blue color due to Cherenkov radiation. It probably is Cherenkov radiation in that. I can't confirm. I don't know what the thing is. Certainly in the reactor core itself, you get Cherenkov radiation, so I assume that you would get Cherenkov radiation from the fission products because it's the same source. Let's see. What else do we got? There's radiation from CRT, from cathode ray tubes, yes. Do they leak electrons? Do cathode ray tubes leak electrons? So that's CRT, I'm assuming you're talking about cathode ray tubes and not critical race theory. Do they leak electrons? I don't think critical race theory leaks electrons, but cathode ray tubes probably do leak electrons because they're firing at a screen, and then some fraction of them would tunnel through the screen. Why use rods? Why used rods are not used to produce energy, for example? Okay, so why don't they use this to do, for example, like an RTG, which we haven't talked about yet, but which is what, a radioactive thermal generator. Those are the kinds of thermal generators that you put on satellites and stuff like that. It's probably just not efficient enough to make it worthwhile. If it becomes more expensive to generate the electricity than what you're doing, than just storing it, then you'll just store it. It's basically all driven by the cost. If something costs more to do, then it probably has a bigger carbon footprint to do it. It might be different in the case of spent nuclear fuel where it's already sitting there and you don't have to do anything to produce it. But there's some infrastructure that goes into making something viable, and if it's not commercially viable, then you've just wasted this infrastructure, and that infrastructure comes in the form of cement and steel and staff and stuff like that ultimately makes it back primarily to fossil fuels. Critical race theory leaks gamma rays. Let's see. So they probably don't use the spent rods as to produce energy. For one thing, it's also on a much, much smaller scale, right? You're talking 10 megawatts for a couple of years, and compare that to a 1 gigawatt plant. 10 megawatts to a 1 gigawatt, it's 1% of the energy. And so if you have to spend an equal amount of money or even a comparable amount of money to get 1%, then it's 10 times less. Let's say that you have to spend 1/10 the amount of money to build a spent nuclear fuel power generator, then it already costs 10 times more than nuclear, and so it's not going to be competitive with anything else. All right, let's see. Another way of saying is that people from Denver have twice the proposed limit. Yeah, people from Denver have twice. So we couldn't live in Denver anymore if you follow that limit. To produce steam. That's a good question. So you could use the fuel rods and just produce steam off of it. So plausible, but you still run into the issue that you're only getting 1% of the energy. So you have a whole turbine that can only produce 1% of the energy for 5 years. All right. So that's what I got for today.